All right, here we go. Unit 4, Lesson 15, Quadratic and Linear Systems. So we're going to be finishing our work on systems of equations by doing a mix and match where one of the equations in the system is a quadratic and another part of the system is linear. So first, let's just make sure we understand graphically what this would look like. Remember that if you have a system of equations, right, one of the tricks that you can do is if you can graph both lines in the system or lines up until today, and if you find the intersection point, you found the x comma y pair that solves both equations. And so the same idea is going to apply today when we have a system where one of the equations in the system, this case f of x, is x minus 4, and the other equation in the system, g of x, is negative x squared plus 4x. So we're calling these f and g, but we could also both call both of these y, right? Y equals x minus 4 and y equals negative x squared plus 4x. So one way that and I'll make this color-coded here to make this even a little bit more straightforward. One way that we learn to solve these, whether by hand or on Desmos, would be to graph these two and find their intersection point. In the first case, we have x minus 4. So we have a y-intercept of negative 4 and a slope of 1. So I'll just kind of plot all of these points here. That'll make the intersection really straightforward to find. So this is the line here, y equals x minus 4. Every y coordinate is 4 less than the corresponding x coordinate all the way along this line. I can draw that a little better. All the way along this line. Now, we have as our second equation, negative x squared plus 4x. I'm just going to plug in some numbers to think about this. If x was 0, y would be 0. If x was 1, well, we'd have 1 squared is 1. We'd have negative 1 plus 4, so that would be 3. If x was 2, we'd have negative 4 plus 8. We'd have 4 there. If x was 3, we'd have negative 9 plus 12. We'd be back to 3. Okay, I think I found the vertex. If x was 4, the output would be 0. I'm basically just working through here. You could totally use a calculator to help you find these. Just working through what these look like. And so I think I already found one of the intersection points, right? I think I found one of these intersection points at 4, 0. And let me just go a little bit further to try and find the next one. If x was negative 1, we'd have negative 1 squared plus 4 times negative 1. This would all work out to be negative 5. Right, the plotting, I don't want to get too hung up on that. You can use a calculator to help you. You could use Desmos to help you, right? But the idea here is that these two equations share two input-output pairs in common. 4, 0 and negative 1, negative 5. And what I want to emphasize here is if you have this system, you could also, and so yeah, there's our answers there are 4, 0, and negative 1, negative 5. But what I want to emphasize here is that you could also do this without a graph. If I just gave you this as a system, y equals x minus 4 and y equals negative x squared plus 4x, we could use the substitution method. If both of these right-hand sides are equal to y, alternatively, plugging in x minus 4 for y in the second equation because it is the same thing as y, we could write x minus 4 is the same thing as negative x squared plus 4x. And we could solve this equation. When you see an equation that I've asked you to solve and it's got both x squared and x terms in it, the light bulb should go off. Okay, we're not in Algebra 1 land anymore. I can't just get all my x's to one side and my numbers to the other because I'll have x and x squared. Like they're not going to combine. So this is an Algebra 2 solve. Your goal is to get everything in the form ax squared plus bx plus c all equal to 0. And I want this a to be positive to make it easy to factor. So I'm actually going to bring everything over to the other side. So what we're going to do, we're going to add x squared to both sides. We're going to add x squared to both sides, and we're going to subtract 4x from both sides. We're going to subtract 4x. So what we are left with there, and I'll give myself some more room here, we're left with x squared plus x minus 4x is equal to 0, So this is what we have here. Oh, sorry, not minus 4x, minus 4. Sorry, that should come off the x there. So we're going to have x squared, x squared minus 3x minus 4 when we bring everything over. And all of that's going to be equal to 0. And so we could have factored and solved this as x minus 4 times x minus 1 equals 0. And so that would give us these same x coordinates to our solutions. I would know that the x coordinates are x equals 4 and x equals 1. The only thing left to do would be to take this 4 and 1 and plug it back in to one of these equations to figure out what the y values would be. And in this case, if you plug in 4, 4 minus 4 is 0. If you plug in, this should be a plus 1 here. And so this would be x equals -1. If you plug in a -1, this would be -1 comma -5. And so you'd get these same two solutions. The only other thing to watch out for here is that if you just kind of think about this graph, well, you can imagine if I had moved this red line up, right? If I had moved this red line up, maybe I could move it in such a way that there would be exactly one solution, or maybe I could move it even farther in such a way that there would be no solution. So you are not guaranteed to have a solution here in the way that you are with two lines. And so let's see what that would look like. So same process here. If we have these systems of equations, and again, both of these you can imagine are y, so we can set these equal to each other. If we set x plus 4 squared minus 3 equal to 2x plus 4. To solve this, I need to first expand this out. X plus 4 squared, which is x plus 4 times x plus 4. I'm just going to do that over on the side. X squared plus 8, well, I'll do it all the way out. Plus 4x plus 4x plus 16. X squared plus 8x plus 16, okay? X squared plus 8x plus 16 minus 3 is equal to 2x plus 4. A lot going on here, but if we take 2x away from both sides, and we take 4 away from both sides, take 2x away, take 4 away, what we're going to be left with here is x squared plus 6x. We'll have 16 minus 3 is 13, minus 4 is plus 9 is equal to 0. And so when you factor this, you get x plus 3 times x plus 3 equals 0. And so it's actually the same value in here. X minus 3 is what would make either of these parentheses 0. It would make both of them 0. So this would be the case of something only having one solution. So it would be like if we had a quadratic like this and what we're going to call a tangent line, it just barely touches, that only has one solution at x equals -3. And so we need to plug in to see what the y coordinate is. If I plug in here, 2 times -3 is -6, plus 4 is -2. So the solution here would actually be -3 comma -2. So that is one possibility there, is that you can have a single solution instead of two solutions. What we could also see is the following case. If I have this system of equations, so I set these right-hand sides equal to each other, -1/2 x plus 4 is equal to -x squared minus 4x minus 2. I want to make this a positive x squared on the other side. So I'm going to add x squared, I'm going to add 4x, and I'm going to add 2, add 2. What I would have here is x squared plus 3.5x plus 6 is equal to 0. And it might not be immediately apparent, but there is no way to factor that expression. There's no two numbers or even decimals that multiply to make 6 that add to make 3.5. What I would appeal, the logic I would appeal to here is I want you to just kind of imagine what this looks like. This is a quadratic function that has a y-intercept at 6. And when we go to graph this, if you were to look at this graphically, right, if you were to actually like go ahead and plug in these graphically, what it would look like is something like this. And it would never touch, this would never touch the x-axis. It would have no zeros. So if you get to one that's not factorable, you would just have no solutions. And so what that would be here, it would be like if you had a quadratic and a line that never touched and you had no solutions, okay? So I'm just gonna show you one more here just to really solidify this. Those are not the most common cases. I want you to see one more example, exactly how it looks on the Delta Math here today. Find all the solutions to the following system algebraically. So without using a graphing calculator, write your solutions as coordinate points. So step number 1 is to get both equations in standard form by solving for y. Equation number 1 is already in standard form, but equation number 2, I want to subtract 2x from both sides and turn it into y equals 11 minus 2x. Because now I know that 3x squared minus 2x minus 1 and 11 minus 2x, if they're both equal to y, they are both equal to each other. So I can use the substitution method and substitute in 11 minus 2x for y. So I'm going to write that down here, 11 minus 2x. I gave myself a lot more room here than I needed. 11 minus 2x is the same thing as 3x squared minus 2x minus 1. That's what doing that rearranging tells us. And so now we're going to move everything to one side. In this case, I want to go to the right because I want to keep this a positive 3x squared. So I'm going to add 2x and add 2x. I'm going to subtract 11 and I'm going to subtract 11. So what we have here is 0 is equal to 3x squared. Oh, this is interesting. There's actually not going to be a middle term. 0 is equal to 3x squared minus 12. So this is a good one to work on, because when we go to factor this, it is factorable, right? There's two things that we need to do first. First, factor out the 3 as a greatest common factor, 3 times x squared minus 4, and then to recognize that this is the difference of two squares, because you have a perfect square, you have x times x is x squared, and you have another perfect square, 2 times 2, and we are subtracting them. So this factors actually as 3 times x plus 2 times x minus 2. So the two x values that make this a true statement are x equals negative 2 or x equals positive 2. Finally, I should have written this as a fourth step here. Step 4 is to plug in for y, right? You want to plug in to find the y coordinates of each of those. And so we know here from our original, we know y is equal to 11 minus 2x. So we'd have y is equal to 11 minus 2x. In the first case, our first y value, y1, would be equal to 11 minus 2 times positive 2. So 11 minus 4, that's 7. So we have final answers here. One of them is 2 comma 7. Then we would do the same thing plugging in negative 2. y2 is 11 minus 2 times negative 2, or 11 plus 4, that's 15. So our other solution would be negative 2 comma 15. So these would be our two solutions. In Delta Math, you're going to enter these both as coordinate points. So you'd have 2 comma 7 and you'd have 2 comma 15. Sorry, negative 2 comma 15.